So we've been looking at time travel and time dilation, and hopefully, Daniel, I've convinced you, yeah, weird stuff is going on with time. Why don't we notice it in our everyday lives? Put your pencils down, look up. So you're going to start to see some short videos by a professor named Brian Greene. Brian Greene teaches at Columbia University. He's often on talk shows. You may, when you see him, say, oh, I've seen that guy. He's also in a few big series like on PBS. He's one of the world experts on Einstein and special relativity and general relativity. So the first question we want to ask is, how fast does time slow down?
When Einstein realized that time elapses more slowly for an object in motion compared to the rate at which it elapses for us here on a stationary clock, he didn't just make a qualitative statement. He made a quantitative statement. He wrote down a formula that tells us how much more slowly time will elapse on that moving object. And if you like equations,
Who doesn't like equations? Why would you say if you like equations? Everyone loves equations. No? Okay.
slowdown formula is 1 over the square root of 1 minus v squared over c squared. V is the speed of the object, c is the speed of light. But if you don't really like formulae, let me show you that equation in action just through some visual illustrations. So here is a stationary clock with us on Earth. Here's a clock on a spaceship. Now, if the ship is not moving, the two clocks tick off time at exactly the same rate. But now, let's give that spaceship some velocity. 1,000 miles per hour. You know, reasonably quick speed. Notice that the slowdown, while there, is just too small for us to see it. That's why we don't know about this slowdown at everyday speeds that we...
So, 1,000 miles an hour is pretty fast, but it's there. You can't notice it.
Can achieve. But let's take this 1,000 miles an hour and kick it up to a much higher velocity. 100 million miles an hour, about 1/6 of the speed of light, fast enough to go around the entire Earth in a single second. There is a slowdown on that clock. If you look really closely, kind of squint, you can kind of see it, but still, even at this very high speed, difficult to see, not a big slowdown. So let's kick up the velocity of the ship even higher. Let's bring it to 600 million miles an hour. The speed of light is about 670 million miles an hour. Now, at this speed, the slowdown of time becomes obvious, right? This clock is ticking off time much slower than our clock here on Earth. And just to see it even more starkly, let's bring that speed of the ship even higher. Let's put it at 668 million miles an hour, just below the speed of light. And look at how time is elapsing on the spaceship clock. Very slow compared to the rate at which time elapses on our ordinary clocks here on Earth. And this really illustrates quite wonderfully how we don't know about the slowdown in our bones intuitively because we never achieve speeds anywhere near the speed of light. But if routinely we did travel at speeds near the speed of light, this slowing of time would be obvious to us. This dramatic slowing of time near the speed of light would be intuitive. It would be in our bones.
So we don't notice it because at the speeds that we're used to, while there, it's negligible. We ignore it. Why don't we notice special relativity in our everyday lives? First of all, let's write out the time dilation equation, please. So write down T equals T0 all over the square root of 1 minus V over C all squared. And Daniel, you'll help Shane along the way because he just jumped into some of this. You can point out where you're looking and things like that. Thank you. And what I'd like all of you to do, please, circle the square root. The square root of 1 minus V over C. That expression has a special name. We call it the Lorentz factor. It's named after a mathematician. Before Einstein published his paper in 1905, a mathematician around 1895 had already discovered that factor. He said, look, I can't explain why, but it turns out if you multiply the times by this, the numbers will balance out now. So we've named the factor after him, the Lorentz factor, but because he couldn't explain why, we don't give him credit for special relativity. He had just done the math and said, this seems to be what works. We abbreviate the Lorentz factor with a Greek letter gamma. What's a Greek letter gamma? It looks like a skinny fish doing a headstand. So you all learn when you're a child that you can draw a fish like that. Make it skinnier, put it on its head. That's a Greek letter gamma. And so rather than writing that square root, I'm going to start to abbreviate it with the gamma symbol, which means, Ava, I can write the time dilation equation as T0 over that. And I think I gave you that version on your formula sheet as well, he says. Yeah. I'm going to start to abbreviate. First of all, of course, I'm going to start to abbreviate. I hope you've learned that about me, that if there's an abbreviation, I'll take it. And also because, it's a Greek letter, that gets my little math nerd heart going pitter-pat as well. Absolutely. So I'm going to start to replace that square root 1 minus v over c all squared with the little gamma symbol, and then I'll write the numbers in, but I won't write out the generic one. Just letting you know. But let's look at this. Specifically, let's start to look at a situation where we have 1 hour of time all over 1 minus v over c all squared. You can write that version down if you want, or you can just look at it on your green sheet. I'm putting it here, and what we'd like to do now, rather than write out a bunch of stuff, is I'd like you to get your calculators out and follow along with me, please. We're going to ask, first of all, how much is time dilated for a human walking at 2 meters per second? Ethan, is this a percentage of the speed of light? Did I give this to you as a percentage of? So we can't go, do you see, do you see, do you see? We're going to have to type this in. So what's V as a number exactly? Get your calculators out. And what we're going to do is we're going to do this in chunks. I'm going to type inside the little tiny bracket first. I'm going to go 2 divided by, what's C as a number exactly? What's C as a number exactly from your formula sheet? So I'm going to go 2 divided by 3 times 10 to the 8th. That's inside the bracket. All of you right now, if you hit equals, should see 6.6 times 10 to the negative 9, or you might see 0.00000000066. Yes, everybody has that? We move outside the mini bracket. What's just outside the mini bracket, Ethan? What's just outside the mini bracket? Squared. So hit your x squared button and hit equals. Now what do we do? 1 minus that. Yes? So I'm going to go 1 minus answer button. Right, Andrew? We're doing that now. Okay, so you join us in the next one, because I'm not going to redo it. Everybody who's with me, hit equals. Wait a minute. What'd you get? Did you get a 1? Is it really a 1? Is 1 minus something actually 1? No, it should be 0.999999999 and something. But unfortunately, even your decent calculators, this is so small that they're already caving and say, yeah, I'm not tracking that many decimals anymore. Oh, and then you would go the square root of 1. What's the square root of 1 in your head, everybody? And then you would go 1 divided by 1. What's the 1 divided by what in your head, everybody? Basically, when you're walking, what's the time dilation factor? The same. Technically not. And if you want to find out what the actual answer is, do a Google search for long number calculator, and you'll find some web pages that have scientific calculators that'll go to like 50 sig figs, and you'll be able to get an answer. But yours only go to about 15 sig figs, and they just conked. So then I thought, well, let's go faster. Let's go on a race car. So now, Andy, we're going to repeat this. Clear your calculator. Andrew, how fast are we going in the second one? So let's go 70 divided by 3 scientific notation button 8. And then hit equals. And you should see 2.333 times 10 to the negative 7, or you might see 0.000000233. I don't know. Yes? Then what? Squared? So hit your x squared button. I got 5.4 times 10 to the negative 14. The 4s repeat. Yes? Then what? 1 minus that. What do you get when you hit equals? Yeah, my calculator conked out on me again. I was a little disappointed. I thought it might get this one. But even in a race car, although technically time is moving slower for you, it's negligible. Is that okay, Daniela? So I started to think, well, how else do humans travel fast? The SR-71 is the fastest jet ever built. It traveled at 1,000 meters per second, a kilometer a second. So I said, well, let's repeat this with that. So I'm going to go 1,000 divided by 3 scientific notation button 8. Got that? Follow along on your calculator. I hit the x squared button. I went 1 minus answer button. And I was disappointed. I thought, wait a minute, 11 decimal places, I thought I would get an answer by now, but no. Oh, and then the square root of 1 is 1 divided by 1. It's still the same. I was a little grumpy on this one. I went, okay, well, how else do humans move fast? I said, wait a minute, the Earth is not at rest. Technically, the Earth is a spaceship relative to the sun. So I said, the Earth moves around the sun at 29,600 meters per second. So, Nick, I said, let's put that in for V. So, clear your calculator. Try going 29,600 divided by 3 scientific notation button 8. You did. Squared. I get 9.735 and then a bunch of ones. 1 minus that. Oh, hey, I didn't get 1 this time, so now I'm going to keep going. What's the next thing? I think now it's square root of that. Yes? Square root answer button. And then 1 divided by that. And I did get an answer. I got a 1, 8 zeros, and a 5. So what does that mean? That means for every hour that goes by on Earth, 1.000000005 hours go by on the sun. A little bit more time goes by on the sun. Okay. 1.1234567 zeros and a 5. Or for every second that goes by on the Earth, 1.000000005 seconds goes by on the sun. Because the question says hours, but remember, Einstein's equations are unit independent. So days, years, seconds, that's the ratio. I thought for a while, Alisher, oh, you know what else moves fast? The Earth and the Sun, our solar system is also a spaceship. It's moving around the Milky Way. We believe there's a black hole at the center of the Milky Way called Sagittarius A star, and we think the Milky Way is revolving around that. And we can calculate how fast we're moving. 2.1 times 10 to the 5th. That's faster. So I said, let's try plugging that in. 2.1, scientific notation button 5, divided by 3, scientific notation button 8. I got 7 times 10 to the negative 4, or you might have got 0.0007. Squared. 1 minus that. Square root of that. 1 divided by answer button. And I got 1, 2, 3, 4, 5, 6 zeros. I got a 1, 6 zeros, and a 2, 4, 5. But again, would you notice that? that for every second that goes by Yosef, if he's on the Earth, Ethan, who's on that black hole, would be aging by 1.0000245 seconds. Not really. By the way, someone pointed out to me last class, and they're correct. This would be if you were close to the black hole. Gravity also changes time. So if you were really close to the black hole's gravitational field would dominate what was going on, and this number would be very different. So you're nearby, maybe you're orbiting the black hole at a fairly healthy distance away. It was a good nerd point. All right, let's go faster. Trevor, UBC has a particle accelerator. They have a cyclotron where they accelerate protons to 2.24 times 10 to the 8th. Now we're getting times 10 to the what, Trevor? That's a fraction of the speed of light now. Now we should notice it. So let's go 2.24, scientific notation button 8, divided by 3, scientific notation button 8. Now what, Trevor? But now what am I going to do? Yeah, I got 0.746 repeating. Squared. 1 minus answer button. Square root of answer button. 1 divided by answer button. For every second the protons experience, how many seconds go by for the researchers who are standing at rest? Anyone? Trevor? Yep. For every hour that the protons experience, how many hours go by for the researchers who are standing at rest? Yeah. Here's our time dilation factor. Now that's probably noticeable. In fact, it is. It's noticeable enough that the researchers, if they're doing things like looking at radioactive decay and how the particles break apart, they have to use the time that the particles are experiencing. They cannot use their own reference time. Otherwise, none of their experiments work. So this is one way that this has been proven in real life to be a thing. CERN, that's where the Large Hadron Collider is. It's in Geneva, Switzerland. It's the world's largest particle accelerator. They can get muons up to 2.996 times 10 to the 8th. Okay. 2.996, scientific notation button 8, divided by 3, scientific notation button 8, squared. 1 minus that. Square root of that. 1 divided by that. Oh, I get 19.4. Now we're talking. So for every second those muons experience, the researchers experience 19.4 seconds. Or if they're planning on doing an experiment where the muons experience 1 hour of time, they better have people in the building for 19.4 hours of their time. Otherwise, they can't do the experiment. When I typed these up about 10 years ago now, the fastest we could get anything was at the SLAC, the Stanford Linear Accelerator. We can go faster now. Because they improved the Large Hadron Collider, and so I need to go look up the numbers. But at the time, this was the fastest we'd gotten anything to go. What's the time dilation factor there? 2.9979. Scientific notation button 8 divided by 3, scientific notation button 8, squared. 1 minus that, square root of that, 1 divided by that. And I get 26.7. So, in answer to the question, Caden, why don't we notice this in our everyday lives? Do you notice it's basically, I graphed, by the way, the Lorentz factor I graphed the speed of light versus the Lorentz factor versus the speed of light. And Caden, do you notice even at half the speed of light, it's still pretty flat? It's there. Even at 3/4 of the speed of light, meh. It's really only when you get closer and closer to the speed of light, that's when it becomes dramatic and you're arriving home and you're younger than your own child. Duck. Yeah, Caden. Can I see time dilation illustrated within 10 seconds? Okay. Put your pencils down, look up. This is actually a physics joke, so here's physics humor. Are you ready?
This video would be 10 seconds long if you watched it while your computer was whizzing past you at 87% the speed of light.
How long did this video actually take in seconds in our time frame? But if it went past you at 87% of the speed of light and you had Superman eyes, time would be exactly slow enough on the spaceship that it would not take 5 seconds. It would take what? 10 seconds. That's a physics joke. Okay? I'm telling you, at the special relativity conferences, this would have them rolling in the aisles. That's so class funny! No? Okay, bonus. At that speed, your computer would also look something like that picture. You can't see the video because the colors would be redshifted too much. So we've talked about time travel. There are other ways to time travel as well. I have here a video. It's called 3 Easy Ways to Time Travel and 3 More Exotic or More Difficult Ways to Time Travel. Put your pencils down. Here we go.
Time travel can be complicated and complicating, so let's ignore all the paradoxical stuff and talk about a few simple ways that you can time travel without leaving your home. First, do nothing. You're already traveling through time. I mean, here you are, 15 seconds into the future since the start of this video.
That's kind of a cheap one, but first of all, everyone is a time traveler because, watch, you just traveled through a second. You're embedded in time. But I think what you mean, Nick, for time travel is you would like your time to be different from everybody else. That's what you mean by traveling through time. Okay.
Easy, right? The point is, we're all always traveling forwards through time. But that's boring time travel. What's interesting is time travel relative to other people. To do that, start walking, and you'll travel through time relative to someone standing still. We've known for over a century that time and space are really just 2 components of a single space-time, and the faster you move, the slower time will pass for you. If you take a walk around the block, you'll be 3 femtoseconds younger than your friend who stayed home.
That femtoseconds, he used a long number calculator because when we tried calculating it, we ended up with exactly a 1. We got the same time ratio. But no, if you're moving relative to the people back in your house, technically you are aging slower. You are technically traveling through time, but barely.
Except in order to walk around the block, you had to stand up. You're now further from the Earth, and so gravity is a tiny bit weaker for you, which means you're traveling through time relative to your friend who's sitting down.
This is what the movie Interstellar was getting into when it was talking about their time dilation. It turns out because of general relativity, gravity affects time. The weaker gravity is, the faster time is. I think that's the way it works. So right now, my head is further from the Earth than my feet. Gravity is a tiny bit weaker on my head than on my feet. Therefore, my head is in a slightly different time zone than my feet. My head is traveling through time relative to my feet. So, you want to travel through time? Stand up.
That's right, more gravity makes time slow down too. If you stand up for a minute, your feet will age 10 femtoseconds less than your head. On the other hand, GPS satellites high in orbit experience less of Earth's gravity and thus travel noticeably faster through time than we do, which is why their clocks are calibrated to run slow.
All right. Let's get into the complicated methods. Are you ready?
But maybe you want to time travel more than a few femtoseconds. Get ready for your head to start spinning. I mean, the universe. Because if the whole universe were spinning really fast, general relativity predicts there would be time loops all over the place. Moving along one of these loops, you'd always feel like you were moving forwards in time, but overall you'd loop around and travel back to a time and place in your own past. It's a little like how you can keep moving forwards on the Earth, but Earth's curvature brings you back to where you started. Unfortunately, our universe isn't spinning. Maybe it would be easier to build an infinitely long, super dense spinning cylinder, which would also curve space-time enough to create a time loop. The problem, of course, is how do you build something that's infinite in size? Maybe you could just make it really, really big. No. If you tried to squeeze this time machine into finite space, you'd need negative energy, something nobody knows how to create, to make it work. Otherwise, you'd end up with a black hole. Wait, but what if instead of a black hole, we built a wormhole? Wormholes are hypothetical, but not physically impossible, bridges through space-time. Shortcuts that can instantaneously connect two different places and times in our universe. If you had a wormhole, you might be able to use it to travel into the past or the future. The problem is that no one knows how to build a wormhole, or once you've built it, how to keep it from collapsing. As Sean Carroll has eloquently written, keeping wormholes open requires a form of negative energies. Nobody knows how to make negative energies, although they occasionally slap the name exotic matter on the concept and pretend it might exist. Well, that's too bad, but as a consolation, welcome to the future. Almost 3 minutes have passed since the beginning of this video, and we now have personal jetpacks.
All of that was the setup. Now let's get to the lesson. Turn the page. I promised you weirdness and strangeness, Julian. It turns out not only is time affected because the speed of light will always be a constant, it turns out Einstein's theory of special relativity makes predictions about length and mass as well. I'm not going to do a mathematical proof. I'm just going to tell you the prediction it makes for lengths. It says this: the length of an object is measured to be shorter when it's moving than when it's at rest, but this shortening is only seen in the same direction as its motion. If the length of an object when it's standing still is L0, you know what I think, how I remember this? I think LO is the original length at rest. Oh, Trevor, if you're at rest, what's your velocity exactly as a number? So here's how I remember. L0 is the original length at speed 0. Whichever one of those two you want to use to help you remember which one is meant by L0, go ahead. And here's what it says. The relativistic length, the contracted length when it starts to move, can be calculated by going L0 times the square root of 1 minus V over C. Also, you know what? It can be calculated by going L0 times the gamma function. Where, again, L0 is the original length at rest, and L is what we call the relativistic length. And you can put in brackets, it's the shorter one. Lengths contract. They get shorter. If you have two lengths and you're not sure which is which, the shorter one has to be L. As an illustration then, if a baseball went whizzing past you, the faster it was whizzing past you, the more its length would contract in the direction of its travel. Shane, if it was traveling at 87% of the speed of light, it would look like that. If it went whizzing past, and you had Superman eyes so you could see it. If it went traveling past you at 99.5% of the speed of light, it would look like that. If it went traveling past you at 99.9% of the speed of light, it would look like that. Ooh. What would it look like if it went whizzing past you at exactly the speed of light? We'll come back to that. So let's do one. Example 1. I like example 1. I like example 1. How long would a meter stick appear to be moving if it was moving past you with a speed of 99.5% of the speed of light? Yosef, what's this question asking me to find? Which length? L or L0? That's the question. The moving relativistic length? Good. Let's go L equals question mark. That must mean they told me L0. Captain Obvious, what's L0 if it's a meter stick? Thank you. It's amazing how many. They didn't tell me L. It's a meter stick. One. Oh, just like the time dilation equation, the length contraction equation is also unit independent. If you put in meters, you'll get out. If you put in kilometers, you'll get out. If you put in yontas, you'll get out. Whatever the heck those are, right? What's our speed?
0.995 c.
Okay. The length contraction equation says L equals L0 times the gamma function. Where L0 is 1 times the square root of 1 minus 0.995 C over C all squared. Yosef, do you see? Do you see? Do you see? What do you see? Now, that's kind of convenient. What do you get? So here is our meter stick. Let's suppose it's whizzing to your right, that way. How long would it be in your universe? How long would you see it appear to be if you had Superman eyes? This long? This long? No, I think you get 0.09. You know what? You get 0.1 if you round off, I think. Yes? Yeah. 0.1. Look up. 0.1 on this meter stick is right there. It would be, sorry for those of you on YouTube, it would appear to you in your universe to be this long. You would see the writing all smooshed together, like very, very skinny. The vertical height wouldn't change at all, so it would look like a very short and stubby meter stick. Yeah, ready for the weirdness? I promised you some weirdness. Let's suppose I had a tunnel that was half a meter long, 0.5 meters long. Okay? At rest, if I put this meter stick in the tunnel, it would stick out on either end. Yes? But if it was moving at 99.5% of the speed of light, it would easily fit inside the tunnel. It would completely vanish inside the tunnel, and you wouldn't be able to see it. You could close the gate on either end of the tunnel, and it would fit inside the tunnel, even though the tunnel is only 0.5 meters long. What would happen if it suddenly came to a stop inside the tunnel? That's a good question. We'll have to dive into some of the weird things that this involves. But that's for another lesson. So 0.1, is that right? Okay. Example 2, an 85-meter long spaceship passes you at 2.23 times 10 to the 8th meters per second. How long does the spaceship look to you? Alisher, what's this question asking me to find? Length, which one, L or L0? So I had to think about this for a while, and I said, wait a minute. It's asking how long it looks to me. Am I moving? No, you know what? I think that 85 was how long I saw it at rest. The spaceship is moving. It wants me to find L, the relativistic length. So I think this question also wants me to find L. What was L0? No, read the question carefully. Yes. And I guess V, we can't do our do you see. We're going to have to put in the 3 times 10 to the 8th. Here we go. I'll write out my shorter version of the length contraction equation. I'm going to use the gamma as my abbrev. And it's going to be 85 times the square root of 1 minus 2.23 times 10 to the 8th divided by 3 times 10 to the 8th all squared. Alisher, I can't go, do you see, what do you see? But I can go, do you 10 to the 8th? Do you 10 to the 8th? Do you 10 to the, what happens to the 10 to the 8th? We can cancel those out at least. Okay. So it's going to be 85 times the square root of, and then 1 minus in brackets, 2.23 over 3 all squared. Now, here's what I do know. The spaceship will be shorter, so you have to get an answer less than 85. If you get an answer more than 85, you probably mixed up L and L0 accidentally. Nick, what'd you get? I'm going from memory. I think it's in the, is it in the 50s? I think. Still typing? Okay. That's okay. Alisher, what'd you get? Nope. Don't divide it. Oh, you should be able to backspace and change it to a times, and if you have a good calculator like your teacher told you. 56.9? What about the people on board the spaceship? would they notice that their spaceship was all stubby and short? Why not? Well, actually, because they're not relative to them, the spaceship is at rest. And so they will experience the 85, the L0, at rest. Now, you, with your Superman eyes, will not only see a shorter spaceship, but if the spaceship was made of glass, you would also see the astronauts moving slowly compared to you. Will the astronauts notice that they're moving slowly? No, because again, relative to each other, they're all at rest. They're all in the same time frame, and so they won't notice that a second isn't a second, isn't a second, isn't a second. You will in your reference frame. Yes. Pardon me? That's a great question. That was the question that I was terrified somebody would ask. Did you hear what he asked? So would they see you moving quickly? Because Mr. Dewick, wait a minute. Couldn't they pretend that they are at rest and that you and the universe are moving past them? Wouldn't they see you all skinny, Mr. Dewick? Wait a minute. Wouldn't they see time moving slower for you? But you said time was moving slower for them. I'll give you an answer, but I can't give you an answer for a couple of days. That's really what's called the twin paradox. And it says, wait a minute. If it's all relative, these should cancel each other. Because right now I've been saying the spaceship is moving and experiencing time differently. But wait a minute, Mr. Dewick. What if the spaceship pretends it's at rest and it's the Earth that's moving? Shouldn't the Earth be experiencing a slower time? The answer is no. And one of the reasons why is because for this to work, the spaceship has to turn around and come back. And when it turns around and it comes back, it's actually entering a different time frame. And technically, there was also a brief moment of acceleration because it changed directions. And that's why the spaceship is the one that's affected by the time dilation, not the Earth. And that's also technically a wrong explanation. I have to dive deeper into it another day. Figured it'd be you. Only this block, only you. Everyone else swallowed everything that I've told them and didn't think deeply enough about the paradox that's hidden in there, but you did. Yeah. Okay, fine. Riley, what's example 3 asking me to find? Speed, technically, but sure. Look at your green sheet. Did I give you a version of V that also has lengths in it? I hope. I did? Okay. Read me that one. It's going to be C times the square root of 1 minus, is the L0 on the top or on the bottom? I can't remember. Bottom? So L over L0 all squared. Okay. It says give your answer as a percentage of the speed of light. So I'm going to leave the C as a C. It's going to be the square root of 1 minus L. Oh, Mr. Dewick said it gets shorter, so it's the 25. The 100 goes on the bottom, squared. So I'm just going to go the square root of 1 minus bracket 25 divided by 100, close bracket, squared, close bracket. And I get 0.9682458. I'm going to maybe go to 4 sig figs. How about 0.9682? And the C is still attached. Nuji, what percent of the speed of light is that? You got it. Yep, don't overcomplicate it. 96.82% of C. Nuji, what does B want? How would I convert this to meters per second? Oh, what did we say the word of meant? In fact, I'd have to first of all change this back to a decimal. I'm going to use my answer button because it's just sitting there. Of means times. What's C as a number exactly? 3 times 10 to the? In my notes, I'm just going to write answer button times 3 times 10 to the 8th. So when I'm studying, I know what the heck I did. In meters per second, you can write out the whole thing, I'm going to go to 4 sig figs in scientific notation. I'm going to go 2.904 times 10 to the 8th. But if you wrote out the whole thing, I'm fine with that. 2.905, sorry. Meters per second. One more, we're done. I like example 4, I like example 4, I like example 4. Example 4 is the next question. In fact, I did example 4 in the previous lesson already. The fact that I'm doing it twice should tell you, hint, hint, nudge, nudge, wink, wink, I really like this question. We did a question in the previous lesson where we sent a spaceship to, I think it was Proxima Centauri, the closest star to the Earth. Let's do another star mission. A certain star is 15.6 light years away. Light years, is that a measure of time because it has years in it? What does it measure? In fact, do me a favor. Let's put a little d above that 15.6 so that we know. How long would it take a spaceship traveling at 0.95 c to reach the star A as measured by stationary observers on the Earth? Chantel, what does A want me to find? I don't think it wants me to find an L. Because I think L is 15.6 light years. And I did this on purpose. I was mean, how long is that vague English phrase? I don't think it's talking about a distance. Time. Time. So, Chantal, let's write down, T or T0. Now read the question for part A. Because as measured by what? Stationary. They're not moving. Okay. In fact, Chantel, have we launched the spaceship yet? Say no. Have we done any relativistic travel yet? Say no. We're not going to use relativity here. We're going to use D equals VT. We're going to write down what V is, 0.95 C, and we're going to write down what D is, 15.6 light years. And the reason I know that, we haven't launched our ship yet. We need to figure out how long this is going to take Earth time. How would I get the T by itself, Chantel? Good. So I get 15.6 light years divided by 0.95 C. Do you see? Do you see? Do you see? And I get years as an answer. And I'm going to go to my calculator. All of you type this in yourselves. And I get 16.4 and change. And I'm going to store this on my calculator. Double check, please, Chantel. Do you get the same thing? Yep. I'm going to write 16.4, but I'm going to keep this on my calculator. So as far as we're concerned, we have to staff the control room for 16.4 years. If we don't, they might be radioing Earth and there's nobody in the mission control room to hear them. Will the astronauts experience 16.4 years? Yes or no? Will they experience more than 16.4 years or less than? Chantel, what's B asking me to find? Now I'm going to use relativity. That must mean they told me T. That's why, Chantel, we had to do part A first. I'm going to write 16.4, but you know I'm using my answer button. V is still 0.95 C. I already wrote that up here. I'm not going to bother rewriting it. Chantel, can you get the T0 by itself in the time dilation equation? What's my new equation? T0 equals... Is it times? I'm going to abbreviate with the gamma thingy. So it's going to be, I'm going to write 16.4, but I'm going to use my answer button, square root of 1 minus 0.95 C over C all squared. Chantel, do you see? Do you see? Do you see? What do you see? Okay. So I'm going to go answer button times square root of 1 minus 0.95 squared. How many years do the astronauts experience, Chantel? Okay? But I'm going to store this on my calculator too. 5.13 years. Julian, what's C want me to find? There's two ways I can do that. So what I'd like you to do is draw a little line down the middle of your page. Like that. The first way, Julian, would just be to use D equals VT, because the astronauts, as far as they're concerned, are moving at just moving like normal. Except it's going to be T0, because that's how much time the astronauts experienced. How fast is the astronauts' spaceship moving? And T0, I'm going to write 5.13 years, but I'm going to use my answer button. So on your calculator, Julian, just go 0.95 times answer button. And remember, this is that weird thing where we said, even though Earth thinks it's 15.2 light years away, when the astronauts do the trip, how much distance will they experience? Not 15.2, but I got 4.87? In fact, I got 4.871098439. Yes? I'm going to write 4.87. And that's light years. There's another way I could have done this. I could have used the length contraction equation. I could have said, what was the original distance at rest from Earth in light years? 15 point something. It's 15.6 times the square root of 1 minus 0.95 C over C. Don't forget, do you see all squared? And if I type that in, if I use the length contraction equation, 15.6 square root of 1 minus 0.95 squared, close bracket. Nick, I get exactly the same answer, 4.871098439. I get the same thing. Now, that's nice for two reasons. Number one, I never proved this equation with you. We derived the time dilation equation. This one I just gave you. Did we get the same answer doing it two different ways? Yeah. Here we got it using the time dilation equation. That kind of confirms that this equation that I gave you is correct. But this is also the explanation. Why do the astronauts travel through a shorter distance? Because it's all relative. As far as the astronauts are concerned, their spaceship isn't moving. Space is zipping past it. And space then, because space is moving, the distance will contract in the direction of motion. As far as the astronauts are concerned, their ship isn't what's moving, space-time itself is. And so space-time will get shorter and shorter. Instead of 15.6 light years long, they'll measure it to be 4.87 light years long. It's the meter stick all over again. But instead of having the meter stick moving, it's space itself moving past the spaceship. That's the explanation. One more thing and we're done. So what does this mean for an object that travels at the speed of light, like a photon? Well, let's take our length equation again. L equals, I'm going to put L0 in, but square root of 1 minus, if we're traveling at the speed of light, how fast are we traveling? C over C all squared. I'm willing to bet that last time I probably said something like, this is so easy, even Yosef can do it in his head. It's probably Yosef that I picked on, just for giggles. Was it you? I don't remember. Because what's C divided by C?
1.
Squared? 1 minus 1 is?
0.
Square root of 0 is?
1.
Square root of 0 is?
0.
What's 0 times L0?
0.
How much distance do photons experience exactly as a number?
0.
So what does that mean? You may have walked out late at night, Yosef, and you may have looked up at the stars and you may have thought to yourself, wow, the light from those stars traveled 1,000 light years to get here, or 1,000,000 light years to get here, or 500 million light years to get to my eyes. That's relative to you. As far as the photons are concerned, Nick, they left, they arrived, and they didn't travel a distance in between. They didn't travel a distance in between. Or if I want to get all poetic, look up. I've just turned on my flashlight. There are photons streaming towards you. Where are the photons? You might say they're in the classroom. That's relative to you. Because these photons don't experience the concept of distance or location, these photons are everywhere in the universe at the same time. Oh, and I already told you they don't experience time either. These photons are seeing everywhere and everywhen in the universe. They're seeing the Big Bang, and they're seeing the end of the universe, and they're seeing that happen everywhere. Or as I like to say, Trevor, light is special. It has some really unique properties. I promised you a little weirdness and a little coolness. There it was. We're going to pause here. Your homework is the take-home quiz. You've got 10 minutes to work on it.